GMAT Number Properties Complete Masterclass. I'm your guide through this comprehensive tutorial, where we'll explore essential formulae and work through 20 carefully selected problem types. Let's begin this journey together. Here's our roadmap. We'll start with essential formulae across 9 core categories, from divisibility rules to factorials. Then, we'll apply these concepts through 20 GMAT-style problems, including problem solving and data sufficiency questions. Ready? Let's dive in. Let's start with divisibility rules, one of the most tested topics. A number is divisible by 2 if its last digit is even, by 3, if the sum of its digits is divisible by 3. For example, 1 2-3, the sum is 6, which is divisible by 3. By 4, check the last 2 digits. By 5, it must end in 0 or 5. By 6, it must satisfy both rules for 2 and 3. By 9, the digit sum must be divisible by 9. And by 10, it simply ends in 0. Memorize these. They save precious time on test day. Now, factors and multiples. If a number n equals p to the power a, times q to the power b, times r to the power c, then the number of factors is simply a plus 1, times b plus 1, times c plus 1. For example, 72 equals 2 cubed times 3 squared. So factors equal 3 plus 1, times 2 plus 1, which is 12. Beautiful, isn't it? You also have formulas for the sum and product of factors, incredibly useful for GMAT questions. Prime numbers, the building blocks of arithmetic. A prime has exactly 2 factors, 1 and itself. Remember, 2 is the only even prime, 1 is not prime, and all primes greater than 3 are of the form 6k plus or minus 1. To test if a number is prime, check divisibility only up to its square root. For 97, you only need to check primes up to about 9.8. This saves enormous time. GCF and LCM are inseparable twins. The GCF is the product of the lowest powers of common primes. For 12 and 18, 12 is 2 squared times 3, and 18 is 2 times 3 squared. Their GCF is 2 times 3, which equals 6. The LCM is the product of the highest powers of all primes. For the same numbers, LCM equals 2 squared times 3 squared, which is 36. Here's the golden relationship. A times B equals GCF times LCM. Memorize this. Even and odd properties are deceptively simple but incredibly powerful. For addition and subtraction, even plus or minus even is even. Odd plus or minus odd is even. Even plus or minus odd is odd. For multiplication, even times anything is even. Odd times odd is odd. Here's the key insight. If a product is even, at least one factor must be even. This logic unlocks many tricky GMAT questions. Consecutive integers appear frequently. The sum equals n times the average of the first and last terms, which is also n times the median. For example, 3, 4, 5, 6, 7. The sum is 5 times 5, which equals 25. 2 powerful properties. If n is odd, the sum of n consecutive integers is divisible by n and the product of n consecutive integers is always divisible by n factorial. For instance, 4 times 5 times 6 times 7 is divisible by 4 factorial, which is 24. Remainders, the division algorithm in action. The dividend equals the divisor times the quotient, plus the remainder. And remember, the remainder is always between 0 and the divisor. Here are powerful properties. The remainder of a sum equals the sum of remainders, modulo n. Similarly for products. And don't forget cyclicity. Powers repeat in cycles, which we'll explore next. Units digit cyclicity is a GMAT favorite. Most digits repeat every 4 powers. For 2, the cycle is 2, 4, 8, 6. For 3, 3, 9, 7, 1. For 7, 7, 9, 3, 1. For 8, 8, 4, 2, 6. Some have shorter cycles. 4 and 9 repeat every 2, while 5 and 6 repeat every 1. The method: divide the exponent by the cycle length, and use the remainder to find the position in the cycle. Simple and elegant. Finally, factorials. N factorial is n times n minus 1, all the way down to 1. Remember, 0 factorial is 1, and 1 factorial is 1. A classic GMAT question asks about trailing zeros in n factorial. The formula: count factors of 5, add floor of n over 5, plus floor of n over 25, plus floor of n over 125, and so on. for 100 factorial. That's 20 plus 4, giving us 24 trailing zeros. Got it? Now let's apply what we've learned. Problem 1. If the 4-digit number 2x4y is divisible by 36, what is the maximum value of x plus y? For divisibility by 36, the number must be divisible by both 4 and 9. For 4, the last two digits, 4y, must be divisible by 4, so y can be 0, 4, or 8. For 9, the sum of digits, 6 plus x plus y, must be divisible by 9. To maximize x plus y, try y equals 8. Then 14 plus x must be divisible by 9, so x equals 4. Therefore, x plus y equals 12. The answer is C. Problem 2. How many positive factors does 720 have? First, prime factorize. 720 equals 2 to the 4th, times 3 squared, times 5 to the 1st. Apply our formula. 4 plus 1, times 2 plus 1, times 1 plus 1, which equals 5 times 3 times 2, giving us 30 factors. The answer is C. Problem 3. The product of two numbers is 2400 and their GCF is 20. What is their LCM? Remember our golden relationship. A times B equals GCF times LCM. Substituting. 2400 equals 20 times LCM. So LCM equals 2400 divided by 20, which is 120. The answer is B. Problem 4. If n is a positive integer and n squared is even, which of the following must be odd? If n squared is even, then n itself must be even, because odd times odd is odd, so n cannot be odd. Now check each option. N is even, n plus 1 is odd, 2n is even, n squared plus 2 is even, and n minus 2 is even. So the answer is B, n plus 1. Problem 5. The sum of 5 consecutive integers is 100. What is the largest integer? Using our formula, sum equals n times the median. So 100 equals 5 times the median, giving median equals 20. The 5 consecutive integers centered at 20 are 18, 19, 20, 21, and 22. The largest is 22. The answer is C. Problem 6. What is the units digit of 3 to the 47th power? The cycle of 3 is 3, 9, 7, 1, repeating every 4 powers. Divide 47 by 4, that's 11 remainder 3. The third position in the cycle is 7, so the units digit is 7. The answer is C. Problem 7. When positive integer n is divided by 7, the remainder is 3. What is the remainder when 2n is divided by 7? Given n equals 7q plus 3, so 2n equals 14q plus 6. Since 14q is divisible by 7, the remainder is 6. Alternatively, test with n equals 10, 2n equals 20, and 20 divided by 7 leaves remainder 6. The answer is D. Problem 8. How many trailing zeros are in 100 factorial? Use our formula. Count factors of 5. That's floor of 100 over 5, plus floor of 100 over 25, plus floor of 100 over 125, which is 20 plus 4 plus 0, giving us 24 trailing zeros. The answer is C. Problem 9. What is the greatest prime factor of 150? Prime factorize. 150 equals 15 times 10, which equals 3 times 5 times 2 times 5, or 2 times 3 times 5 squared. The prime factors are 2, 3, and 5. The greatest is 5. The answer is C. Problem 10. What is the smallest positive integer that must be multiplied by 72 to make it a perfect square? Prime factorize 72. It's 2 cubed times 3 squared. For a perfect square, all exponents must be even. 2 cubed needs one more 2 to become 2 to the 4th. 3 squared is already even, so multiply by 2. And indeed, 72 times 2 equals 144, which is 12 squared. The answer is A. Problem 11 is data sufficiency. Is integer n divisible by 6? Statement 1. N is divisible by 3. That's not sufficient. N could be 3, 6, 9, 12, and not all are divisible by 6. Statement 2. N is divisible by 4. Also not sufficient. N could be 4, 8, 12, 16. Together, n is divisible by both 3 and 4, so it's divisible by their LCM, which is 12, and therefore divisible by 6. Sufficient. The answer is C. Problem 12. The sum of 3 consecutive even integers is 72. What is the product of the smallest and largest? Let the integers be n plus 2, and n plus 4. Their sum is 3n plus 6, which equals 72. So 3n equals 66, and n equals 22. The integers are 22, 24, and 26. The product of smallest and largest is 22 times 26, which equals 572. The answer is C. Problem 13. 3 bells toll at intervals of 9, 12, and 15 minutes. If they toll together at 8 a.m., when will they toll together again? Find the LCM of 9, 12, and 15. 9 is 3 squared, 12 is 2 squared times 3, and 15 is 3 times 5. The LCM is 2 squared times 3 squared times 5, which equals 180 minutes, or 3 hours. So 8 a.m. plus 3 hours equals 11 a.m. The answer is C. Problem 14. How many prime numbers are there between 40 and 60? Check each odd number from 41 to 59. 41 is prime. 43 is prime. 45 is divisible by 5. 47 is prime. 49 is 7 squared. 51 is 3 times 17. 53 is prime. 55 is 5 times 11. 57 is 3 times 19. And 59 is prime. That gives us 5 primes. 41, 43, 47, 53, and 59. The answer is C. Problem 15. If x and y are positive integers and xy is divisible by 12, which must be true? Let's test each option. Option A. X equals 3, y equals 4, xy is 12, but x is not divisible by 4. Option B. X equals 4, y equals 3, xy is 12, but y is not divisible by 3. Option C. Since 12 is divisible by 6, xy must be divisible by 6. That works. Option D. X plus y equals 7, not divisible by 12. Option E. X equals 3 is not divisible by 2. So the answer is C. Problem 16. What is the remainder when 2 to the 100th power is divided by 7? Find the pattern of 2 to the n. Mod 7. 2 to the first is 2. 2 squared is 4. 2 cubed is 8, which is 1 mod 7. Then 2 to the fourth is 2 again. The cycle repeats. The cycle is 2, 4, 1, with length 3. Divide 100 by 3. That's 33 remainder 1. So 2 to the 100th is congruent to 2 to the first, which is 2 mod 7. The answer is B. Problem 17. How many factor pairs does 144 have? Prime factorize. 144 equals 2 to the fourth times 3 squared. Number of factors is 4 plus 1 times 2 plus 1, which is 15. For perfect squares, the number of factor pairs is factors plus 1 divided by 2. Since 144 is a perfect square, 12 squared pairs equal 15 plus 1, 2, which is 8. The pairs are 1144, 2, 72, 3, 48, 4, 36, 6, 24, 8, 18, 9, 16, and 12, 12. The answer is C. Problem 18. In a sequence, each term after the first is 3 more than the previous term. If the fifth term is 23, what is the first term? This is an arithmetic sequence with common difference t equals 3. Using the formula, an equals a1 plus n1 times t, so a5 equals a1 plus 4 times 3. That gives 23 equals a1 plus 12. Therefore, a1 equals 11. The sequence is 11, 14, 17, 20, 23. The answer is C. Problem 19 is data sufficiency. Is integer n odd? Statement 1. N squared minus 1 is even. That means n squared is odd, because odd minus 1 is even. And if n squared is odd, n must be odd. Sufficient. Statement 2. N plus 2 is odd. That means n is odd, because odd minus even is odd. Also sufficient. Each statement alone is enough. The answer is D. Finally, problem 20. If n is a positive integer less than 100, and n is both a perfect square and a perfect cube, what is the sum of all possible values of n? Here's the key insight. If n is both a square and a cube, it must be a sixth power. Find sixth powers less than 100. 1 to the sixth is 1. 2 to the sixth is 64. 3 to the sixth is 729. Too large. So the possible values are 1 and 64. Their sum is 1 plus 64, which equals 65. The answer is B.